this. So today we're covering our last lesson inside of chapter 3, and that is dealing with solving exponential and logarithmic functions. If you want to look ahead in the book at 3.5 and 3.6, it talks about stuff with modeling. And as neat and fun as those sections are, time-wise, I do need to get to trigonometry. I don't want it to cut out too much time on that. So we are cutting those sections from this chapter. If you, again, want to look ahead in the book and see what's going on there and read up on it yourself and ask me questions, I'm happy to answer them, but it will not be formally covered or tested. So let's get into this. So here's some strategies using the one-to-one and inverse properties to help solve exponential and logarithmic functions. So right away, condense logs if possible. So last section, we talked about condensing and expanding logs. And one thing that's going to make our lives easy when solving is to condense logs. This way, I hopefully only have to deal with one log or one natural log. So, like I said, expanding can be very helpful in calculus, but in solving, condensing is far more helpful. They both have their time and place. Once we do that, we want to isolate the logs or exponents on one side. So I don't care if it's the left side or the right side. It's just like, oh, well, getting my variable on one side. It's the same concept as that. So we will use exponents to undo logs. And then we will use logs to undo exponents. So if that variable is trapped inside a log, we're going to have to kind of just rewrite and okay, whatever the base of the log is, that should be the base of our exponentials. And if we have an exponential, that should be the base of our log. So again, I'm going to leave this up for a quick moment in case you are writing this down. These are 3 very, very helpful ideas. I tried to state them as plainly as I could, but this is the general idea. We're going to work on isolating and solving like we have in the past. It's just how do we deal with those new things like logs and exponentials? Well, they undo each other, just like multiplication undoes division and division undoes multiplication. So let's move on. So we got 2 problems to solve here. So with these, we can do it sort of like a rewriting fashion if we wish. It really doesn't matter. So A says log base 8 of x equals 1/3. So here with this, I notice the base of this is 8. So you can either rewrite this in exponential form or use that. So if I rewrite, my base is 8, and then that would mean my power is 1/3 is equal to x. So basically, I'm asking for the cube root of 8 here. Or we could do it this way. I could say, oh, my log is base 8. So I'm going to put both sides, have that be an exponential where the base is 8. The 8 and the log base 8 cancel out. That's where some of those properties from section 2 come into play. And that gives me x equals 8 to the 1/3. So I don't care if you use the logic like I did in blue with rewriting or the logic I did in green. Both are saying the same thing, albeit in a slightly different order. This said cube root of x equals, or sorry, cube root of 8 equals x, where this says x equals the cube root of 8. So if you do not know the cube root of 8 off the top of your head, or the 8 to the 1/3 power, you can always type it in here. That one's actually not too bad. It is just 2. So 8 to the 1/3, or the cube root of 8 is 2, because 2 times 2 times 2 gives me 8. So here we get x equals 2. Again, it did not matter which way you solved that. So B says 5 to the x is equal to 0.04. So again, you can think of this either as rewriting or just taking the log of both sides. I think for you guys, it's just going to be easier to say, oh, let's just take the log base 5 of the whole thing. So when I do that, that cancels out with this 5 here, leaving me with x equals the log, the log base, my smartboard's back now, yep, log base 5 of 0.04. Now, this is one you guys probably do not recognize right away. I believe the answer should be -2. That's what my gut's telling me. Let's double check that though. So again, I can use the log base 5. If you want to use change of base, great. But remember, we do have under here log base A. We can use that command. So log base 5 of 0.04, yes, is -2. Here's how I knew that was -2 beforehand. If I do 0.04 as a fraction, that's 1/25th. And I said, oh, 5 squared is 25. So if I want it to be 1/25th, it should be 1 minus, or sorry, oh, thank you very much, Mr. Ingram.
You guys appreciate this guy today, huh?
Like that energy, like that energy. Thank you, guys. So here I knew it was 1/25th because 25 is 5 squared, but if I want 1 over it, I just make that exponent negative. So that's how I was able to calculate that in my head. But look, most of these aren't going to be like, oh, I could solve that. I could do that in my head. Because most logs, if it said log base 5 of like 2.4, there's no way I'm getting that off the top of my head, okay? So again, you might end up with ugly decimals like that, but you got it. Any questions about example 1 currently? So this right here is our idea of undoing. Exponents help undo rewriting as exponentials, undo logs. Logs undo exponentials. Just like square roots undo squaring something. Okay. Now, describe how to solve this algebraically. Here with this. Yeah, I can't figure out 10 to what power gets me 90. So here's what we're going to do. 10 to the x equals 90. Essentially, what we can do is take the log of the entire thing. Now, I do not need to write log base 10 here because that's our default base. So the log and the base of 10 cancel out, leaving me with x equals the log of 90. Now, look, like I said, technically you can leave this as this exact answer, say the log of 90. However, I know you guys are still just getting your bearings with these. So log of 90 might not mean much at all to you. Like, okay, that's what the x is, but what does that mean? That's why I'm asking for these. Don't just leave your answers like this. I'd like you to put it in the calculator so you get an idea of the magnitude of that number. Now, I'm going to tell you right now, it's probably going to be in the area of 1.8, maybe 1.9, because I know 10 squared is 100. So I know 10 to something a little smaller than 2 should get me 90. So let's see how good my prediction was by going log of 90. Well, I was a little bit off. I said 1.8 to 1.9. It's 1.9542. So I'd like you to give me 4 decimal places. Good morning, Jada. We are just in the middle of the notes, so I'll fix your attendance in a moment.
Yeah, I have to look for the,
Cool. You can go ahead and take care of that again. I'll fix your attendance later. You're welcome. So, you know, that's why we type these in. Even me, like I have an idea of what it was, but I was still a little bit off in my prediction on my decimal. So not a big deal. Let's just put it down. That's x equals 1.9542. So that's the next example. We're going to get into some ones that are a little more complex. One second, guys. I have a question over here. Yeah, actually, if you scroll down, I gave you that. So that's what it just means, I think. Okay. So the question was related to something a little bit older, so I'm not going to go over that with everybody right now. Let's just go on to example 2 here. Now, example 2 is a little more complex looking, but my goal here is I want to isolate the E by itself, and then we'll go from there. Okay. So here with this, if I had a simple problem that just said x minus 7 equals 59, what would my first step be here? What would my first step be here in this one? Add the 7. Same idea applies here. Get the E by itself. Pretend the E's like this x here, and we're going to work on isolating that. So over here, we said add 7 to both sides. Over here, the exact same idea applies. So that will give me x equals 66, where in this case, that gives me e to the x minus 2 equals 66. So now the e is by itself. Now I can take the natural log of everything. We want to wait until our e, or whatever the base of our exponent is, we want the exponential isolated before we take the log of both sides. So since this is e, I want to take the natural log of both sides. So I'm going to say the ln of this, And over here, that's going to be the ln of 66. So e to the x minus 2. Oh, sorry, the e and ln cancel out. So that's just x minus 2 is equal to the ln of 66. If you want to get your decimal in the end, great, good for you. Right now, I'm actually no, this is easy enough. I'm going to solve it, and then we'll just type the whole answer in there. So if it says x minus 2, I should add 2. So it's going to be x is equal to the natural log of 66 plus 2. Now I am literally just going to type this in the calculator. Natural log of 66 plus 2. Natural log of 66. Honestly, I don't have any good predictions for that. Should be somewhere in the area, a little closer to 4, maybe 3 point something. ln of 66. Whoop. Oh, it's a little bit off. It is 4.18. So again, that's why I want you putting these in the calculator, just to help give you some sense of magnitude to these numbers, because I know that's probably not there just yet. So 6.1897. So again, I like going 4 decimal places. If you're just giving me one, that is not sufficient. I'm going to need a minimum of 2, but would prefer 4. That's equal to, what was that? 6.1897, I believe it was. 8965, so that 5 rounds, so it's 6 up to a 7. Any questions about this problem? So you guys have learned how to solve problems before, and working backwards like this. It's just taking this idea that if I have that exponential, like my logs can help undo that. And if I have logs, my exponentials can help undo that. So here with this, notice both of these say log base 6. If I'm taking logs of the same base and say they're equal to each other, should the insides equal each other? If it's saying the log of the exact same thing? Yeah, our insides will need to match each other. So because they both say log base 6, I can just pull out what's inside the logs and be like, oh, 4x minus 7 equals 8 minus x. So now this is just a simple linear equation to solve. This one should give us hopefully nice numbers. Add x to both sides. 5x minus 7 equals 8. Add 7 to both sides. Yep, this is working out real nice. 5x equals 15. Divide both sides by 5, and x is 3. So this one actually was pretty easy to solve. Just took the insides equal to each other. But that was only because they were both log base 6. If one was log base 7 and the other was log base 6, then we got a much more complex problem to deal with. You won't have to deal with problems like that in this class, but that would be far more complex than we would really need, whereas this isn't too bad. Last problem, this one has an ln. So the first thing I want to do is isolate the natural log. So this is 4 times the ln of x minus 5 equals 28. So I'm going to pretend that this is like a giant X. That's what I want to isolate. If I said 4x equals 28, how do I get rid of the 4 in front? Yep, divide it by 4 and we get 7. So the natural log of 5x equals 7. Now I want to rewrite this with base of e. So since this is natural log, I can basically say, oh, this side's e to that, and this side's e to the 7. Now these conveniently cancel, leaving me with 5x equals e to the 7. If we wish, we can divide both sides by 5 and give ourselves a very exact answer here of x is equal to e to the 7th power divided by 5. Now, e to the 7th power divided by 5, I know you guys have probably very minimal clue, if you have any clue, about the magnitude of that number. I know myself personally, I'm actually struggling a little bit to figure out approximately what that would be. So I'm going to go straight to the calculator. I say e to the 7. Okay, that was off from what I was predicting, divided by 5. So here we get 219.3266. So I was thinking e to the 7 might be a little lower than it was, maybe a little closer to the magnitude of 500, but it was over 1,000. So again, just that's why I want you typing these in so you at least get some sort of idea of how big the number is, because this number is about twice as big as I initially kind of predicted in my head, because I was unsure. So that's why we're using the calculator here. And again, I prefer you go 4 decimal places, but I need a minimum of at least 2. 3266. Awesome. And that's it. Any questions about this right now? So I'm going to be very honest with you. It's probably going to be easiest to do a lot of these log calculations inside of the Desmos calculator, because the Desmos can do that change of base super easy. Other calculators, you can handle it, but I'd say Desmos is probably going to be pretty easy. That's like I showed you how to handle everything. So we do have our homework page 217 through 218. We're going to do 38 through 46 even, and 56 through 64 even. So when we look at these problems, what we see here, I believe the first group deals with, you're going to have to, actually, I'll have the notes look up right here. I do. So I believe the first group was dealing with getting it out of the exponent. So we're going to need to take logs. And the next group, I believe, is solving with logs. So 38 through 46. Oh, wait, sorry. The first group is solving when you have logs and need to solve. The second group is where you're going to have exponentials that we're solving. So just covering both grounds there. If you guys have questions, please make sure you ask. That is our recording. Stop share. Stop recording.